Welcome back. Let's talk about the sun. Our objectives for this unit are going to be to examine the structure and behavior of the sun, to identify and describe different features of the sun, to explain how the sun produces energy, and to describe units based or used to measure distance between the sun and the earth. So, what are some of the sun's characteristics? Well, the sun has an interior part and an atmosphere. So for the interior, we're going to talk about the core, the convection zone, and the radiation zone, starting from the inside and going out. And then for the atmosphere, starting from the inside going out again of the atmosphere, is going to be the photosphere, the corona, and then the chromosphere. Actually, it's the photosphere, then the chromosphere, then the corona. So the location is in the center of the solar system, and its average distance from Earth is about 149,000 or 1,600,000 kilometers. So the diameter of the sun is 1,393,000 kilometers around, and the mass is 1.98 e to the 30th kilograms. So add 30 zeros onto here, and that's how massive the sun is. It's humongous. So the age of the sun is around 4.6 billion years. We can't really get a precise number, but around 4.6 billion is as precise as we've got it thus far. The surface temperature is about 5,500 degrees Celsius, which is hotter than Fahrenheit. Remember that? The composition of the sun is around 71% hydrogen, 27% helium, and 2% other elements, such as like iron and silica. Remember, stars are mainly hydrogen and helium, and you need a lot of hydrogen to create fusion or to have the fusion process go on. So the one of the products of hydrogen fusion is helium, so that's why we have extra helium in there. So here's the sun right in the middle of the solar system. We got Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. We've got a comet in here and that asteroid belt between Mars and Jupiter. And then remember, beyond Neptune is the Kuiper belt, where we find a lot of dwarf planets. Ceres, that little dwarf planet, is right in here in the asteroid belt between Mars and Jupiter. So here's just a nice little picture of all of the structures of the sun. In the middle we've got the core, then outside of that we've got the radiative zone, then we've got the convection zone, and then going on to the atmosphere we've got the photosphere, the chromosphere, and then the corona all the way around it. Okay, so the interior. The interior goes the core, the innermost layer of the sun. It produces energy through nuclear fusion. That's a quiz question. And the temperature is around 15 million degrees Celsius. Then after the core, we have the radiation zone. And this is just the layer of the sun surrounding the core where radiation energy is transferred outwards. So temps range from about 7 million degrees Celsius near the core to 2 million degrees Celsius away from the core. Energy is so dense in the radiative layer that sometimes it takes tens to thousands of years to transfer out from the core to the radiative layer to the convection zone. So then we've got the convection zone right outside of the radiation zone, and that's the outermost layer of the interior of the sun. And it's just convection currents transferring energy outwards towards the surface of the sun. If you remember convection currents, they go like this, and when you get to this part right here at the top, that's where energy is transferred outwards, and it creates a horizontal flow of energy at the top there. So you should remember convection currents from Earth Science A. And this is a much more rapid movement than the radiation zone because it's mostly gases in the convection zone. And the temperature is around 2 million degrees Celsius, which is still extremely hot. So here's the core, and then it slowly permeates through the radiative zone through radiation energy. And then the convection zone is more heat energy, so we're going to get these convection currents. You can see them right here. It moves up and around and comes back down. So it's got this cycle all the time of convection. So that's how the energy gets out through the other layers of the sun. So then after the interior of the sun, we have the atmosphere of the sun, and that starts with the photosphere, which is the lower layer of the sun's atmosphere. It's the only layer that we can see without an eclipse happening, so that gives off white light. It's about 100 kilometers thick, and the temperature is about 5,500 degrees Celsius. When you look at the sun, you see the photosphere. So then we've got the chromosphere, which is the middle layer of the sun's atmosphere. It's about 2,000 kilometers thick, which is a lot or sorry, it's 200 kilometers thick, which is more than the photosphere. And the temperature is around 6,000 to 20,000 degrees Celsius, which again is more than the photosphere. So we're seeing heat go higher as it goes out and is transferred throughout the sun. Then the last thing is the corona. That's going to be the outermost layer of the sun's atmosphere. It expends millions of kilometers into space, all around the Earth, all sorts of different areas. The temperature is about 2 million degrees Celsius, and it's only visible during a solar eclipse. So here you have the corona showing, and that's that solar eclipse. And then this white light right here, that's going to be the photosphere. So, how is energy produced in the sun? Well, it's produced by nuclear fusion, and you all should have some sort of an idea of what fusion is at this point. So fusion is just the process when lighter nuclei are combined to produce a larger, heavier nucleus. So you need hydrogen gas, extreme heat, and extreme pressure. This is a quiz question. You need hydrogen gas, extreme heat, and extreme pressure. So the products are going to be helium gas and energy. An example of this, how to show you how energy is created, or not created, excuse me, how energy is converted through fusion, is we've got 4 atoms of hydrogen. They combine to form 1 atom of helium. That's with extreme heat and extreme pressure. Those 4 hydrogen atoms have more mass than 1 helium atom. So the extra mass is converted into energy during fusion, and then the energy is released through the other layers of the atmosphere. So that's how fusion energy happens. It's really just a whole bunch of atoms converting into 1 atom, which essentially weighs less, or has less mass, excuse me, than those 4 atoms, and then you just turn that extra mass into energy through heat and pressure, and then that energy is released through the sun and then to the Earth and most of the other planets. So here is just how fusion occurs in the sun. You see right here, you've got these 4 hydrogen elements combining to form 1 helium element. We've got free neutrons from those hydrogen elements, and energy is converted into those free neutrons and extra mass. So, solar activity. We've got all sorts of kinds of solar activity. We've got solar flares, prominences, solar winds, and sunspots. So the distance from the Earth to the Sun is about 93 million miles, or 149.6 million kilometers, which is measured in astronomical units. So this should say kilometers right here. And the astronomical unit is just the average distance from Earth to the Sun. And we have an elliptical orbit. I don't know why this is here, but don't worry about that. The elliptical orbit that's why we have an average distance. So it's not the same distance from here as we are from here. So like winter and summer, we saw in the previous slide that it's about 3 million miles closer in January than it is in July. So due to that elliptical orbit, then we measure the average distance from the Earth to the Sun's center. So 1 astronomical unit is 149,597,870 kilometers, and that will be on your quiz. So what are sunspots? Sunspots are dark areas on the surface of the sun that are cooler than the surrounding areas. So they appear darker due to our spectrographs and spectroscopes. They appear in groups, they vary in size, and increase or decrease in number over an 11-year period, and that's called the sunspot cycle. A high period can contain up to 150 spots, where a low period can contain few to none sunspots. Some people think this has a correlation to the Earth's temperature, but there's not a lot of data yet to show a correlation. So then we've got solar flares, which are sudden eruptions of energy from a small area on the sun's surface. They extend into the corona, and they have temps between 10 and 20 million degrees Celsius. A quiz question is going to ask you, how do we send a probe to look at solar flares? Well, you're going to need a probe to be able to withstand 20 million degrees Celsius heat. That's how. They occur near sunspots, so right around those sunspots, you're going to see solar flares emanating around them. They disturb radio communications on Earth by interacting with the ionosphere. That's where we send our radio waves. You should know what the ionosphere at this point is. Essentially what it does is it just goes in, it heats up particles in the ionosphere, they start moving at an excited rate, and our radio communications are disturbed. And then we've got prominences. which are kind of like solar flares, but they make loops. So they're eruptions of material from the surface of the sun that form a loop due to the sun's magnetic field, kind of keeping it in, and they're composed of cool, dense gas. And they also disrupt radio communications. So solar flares and prominences disrupt radio communications. Here is a prominence. If it would just continue out, it would be a solar flare. But here is Earth to scale next to a prominence. So you could fit about, I don't know, probably like 15 Earths inside of this one prominence. Just think about the amount of energy that the sun is creating. So the last solar activity thing that we're going to talk about is solar wind. And essentially, solar wind is just a stream of electrically charged particles that flows outwards from the sun's corona in all directions. So you saw that with the eclipse. It just kind of like goes out like that. It extends well beyond Earth. It extends all the way to Saturn. And it travels about 400 kilometers per second, which is amazingly fast. It distorts Earth's magnetic field, which creates the aurora. We'll talk about aurora in the next slide. And it disrupts satellite communication systems and other electrical systems in the area of the solar wind. If we have high solar wind events, then certainly electrical systems will be disrupted. So here's just a picture of solar wind. The sun's energy is just producing this solar wind, electrically charged particles. They travel along our magnetic field, and they kind of travel along lines in our magnetic field. And you can actually see this. I've seen the aurora in person in Alaska. So aurora, it represents the impact of solar wind on the Earth's magnetic field. As I said, the particles flow along the lines of the Earth's magnetic field. So our magnetic field has lines, and those particles are kind of going to flow along them. Particles collide with gas atoms in the atmosphere, causing them to give off light, like red, blue, green, purple, orange. The aurora is beautiful. It's got all sorts of different colors. And they occur in both hemispheres, the northern hemisphere, which is aurora borealis, and the southern hemisphere, which is aurora australis. So here, this looks like, all of these are Iceland, these four. So this is the northern hemisphere, aurora borealis. You can see you got purple, green, red. Down in here, this looks like the northern hemisphere as well. We've got some orange, some green, purples. It's really beautiful stuff. I have pictures of this that I took a time lapse of while I was in Alaska, and just really blessed to be able to see something like this because they move. You can see the light moving along the lines of the Earth's magnetic field. So that's really something to behold when you actually see it. You know, these pictures are great, but these lights are actually moving. So they're like going across like this. You can see them moving along the lines. It's amazing. If you ever get a chance, check it out. That's it for this unit. If you have any questions, comments, or concerns, let me know as always. Otherwise, have a wonderful week.